So I will talk about the Colmez conjecture in average. So that is a precise Colmez conjecture for a linear variety of CM type. And right now we only have proof when you take the average of all the CM types. So this is a joint work with the Yuan, and also based on UVC. The previous work of Yuan, Wei Zhang, and myself. So this is and also math study. I guess the volume. So today's my lecture is trying to reduce everything from the Colmez conjecture average to some formula or some kind of identity in YZV that I'm going to finish, because this Gurzaglia formula itself needs probably another 3 lectures. Okay, so let's try to review. The first thing, what is the ordinal height? So we start with a Abelian variety over a number field. I assume that this A has so this A is a narrow model. So okay, assume it's semi-stable, semi-abelian. So the spatial fibers are essential torus by abelian scheme. Then I introduce, let me try to fix the notation. So this one is the shift, the vector bundle is the invariant differentials. So this self is a bundle, okay? So we do the notation omega small a.
The question from Paris
will be.
Yes. Yeah.
So when you say
Yes.
neuron model, is it the connected part of the neuron model, or you assume that the neuron model has connected fibers?
Just a connected component.
Okay.
Thank you.
So this one is the highest degree of the forms. Then, so this one has a metric at each place. V of k, you can define a metric. But the following method, the alpha square equals to 1 over 2 pi of g integration of AV or C alpha bar. The method there. So my normalization is already a normalization by Fortins. So it's different than Colmez. And so we have, this is called emission line bundle. In our Keller theory of K. So we define the orbital height of A to be, you normalize the degree L K of Q the degree of this bundle. So this is the orbital height. And one thing, when I put this semi-abelian condition here, to guarantee that this height doesn't depend on the choice. I mean, will be invariant of the base change. If you K replaced by finite extension, this will be invariant. So this height was introduced by Gaussians. And in 3, it is a proof of a model conjecture, test conjecture, Chavarrucci conjecture. And so it's one of the most important invariant in arithmetic geometry. Nevertheless, there is no real method to calculate this height, unless again variety you take up. In this case, this bundle have certain canonical section if you raise the power by 12. So this is the Dedekind delta function. So in general case, you don't have such a thing. So now we can see to the Colmez conjecture. So I will only, roughly speaking, I will talk about Colmez conjecture in average. So what I want to do right now, we assume now A has action by certain CM field. So this E is a CM field of the degree equal to 2G. The G is the dimension of A. So in this case, you have a so-called type. Right? 5, and so let me try and if I assume that 5 is, if I assume that A contains all the conjugates of E, then the type is the inside or the home of E to K. This is the type. Maybe let's try to make this one the complex number. It's easy. Fix the one argument place, for example. So that's the usual way to do. Maybe I'm doing something completely stupid. Let's try to make this one be a complex number. Since I will cover all the types. So let's press this. Let's see here. So this is the type. So the OE X and time in space. The Lie algebra of A is when you action by for E, this is isomorphic to you have the type have a trace. It's given by these types. Fine. So this is called a CM type. See, in this case, your abelian variety is actually defined as a field. So abelian variety A will be defined of a number field. Okay. So if we can choose, we can assume that A has good relation. And OK if you choose K to be sufficiently large. So and then this is a good thing about CM theory. And the formula height of A it does not depend. only on the type phi. So this is proved by Colmez. So we can denote like actual phi here. Then Colmez has a conjecture that this is almost like this a conjecture. But Colmez is some linear combination. Of logarithmic derivative L prime of some representation of Gaussian representations. Roughly like that. So this is a precise conjecture, and so this is a precise form for each phi. And there, so far the known result. So this is proved by Colmez himself for abelian extension E of Q. And by Colmez Young, when degree of E of Q is 4. So basically the two cases are completely proved. One is by Colmez for abelian CM extension, another one by Colmez Young for quartic extension. So what we want to do today is we're not going to prove this conjecture precisely, we just prove the average. So the theorem that we prove today is the following. So the fixed CM type, CM extension, quadratic CM quadratic. Okay. Extension. I mean the F equals real subfield. Then we think about T to the G of the summation for the type for some again variety of type phi for all is phi. So you exactly have so many is equal to negative half derivative of 0 eta 1 to 1/4 log d of f df. So where eta I use notation by A, that is the quadratic character. Associate to the extension E of f of A equals, and d E of f df are not of discriminant of relative extension U of f and f itself. Right? So you have the formula dE will be dE of f df squared. So it's absolutely discriminant.
It is norm of difference?
So there, okay, so I have to be careful. I got f here. So my error function does not have a given part. So LF is finite part of this error function. So LF is theta in the summation of norm of S power A. The A is ideal. So it's also finite part. I don't have a given part here. A few remarks. The first remark we're not going to run there is that the formula stated in the Colmez paper is wrong. Second, say the many thing other reference is wrong. So we're not going to say that, but this is pretty correct. Because there's many things like 2 pi, whatever. Then, so I have, anyway, now I'll write some remarks I can write it there. The first remark that I want to write down is, the reason I want to work on this thing, because Jack Zimmerman came to IS in April 9. He gave a pretty beautiful lecture to reduce the under-order conjecture to the Colmez conjecture average, and but somehow we already have some idea to prove that, but never really written down. So these first things by combining with the recent work of Jacobi Zimmerman. So this one, the theorem, so we have this theorem implies the under-order conjecture. For the Ziegler model space. So the argument is pretty straightforward, and I will not going to discuss this part. And I think he probably will write down some notes like that. The second remark is that there's some announcement by a bunch of people of proving a weak form. So recently there's an announcement. At least I heard the lecture by Von Howard in February, and maybe somebody else gave a lecture too. So by Henrietta Howard, and Gordon, and Pussy, era, then they at least can prove the conjecture. I don't know what's the state of that. So this announcement is February. So maybe right now they can do much better than that. O5, H05, equal to negative half. I guess the 17 term also we have F, E of F, 0 of F, E of F, 0 modular the linear combinations of P, D1 discriminant of E, maybe also the linear combinations of log 2 pi. We are not really sure that that is also possible. And but what I'm trying to say that the proof outlined by Howard is very different than ours, and they somehow using Cooker's construction to calculate the Farnham's height, the average by some orthogonal group, which is really high dimension, maybe 2 to the 2t or whatever. And as you see from, I will outline the rest of my lecture, we only use Schumrad curves. So that's a big difference. Okay, so that's the set. Yes?
Is it 1 over 2g or
1 over 2g. 1 over g. Okay, so now I give you the idea of a proof. The proof will have two parts. So the proof have two parts. The first part of this, what I'm going to talk today, is reduce to calculation of CM points on Potential Shimura curve. The second part will be YZZ revisit. So you have to read my book, then I'll tell you how to do that. But of course, I have a manuscript in the hand. The manuscript should be ready in a few days. Okay, so this is something I'm going to talk today. I mean, I can talk about that. This is not fun at all, very technical. So this is probably the more fun part. The key idea of a proof is to play with the heights, calling the heights. So it's like a magical cube. You decompose them in a small piece, then regroup them so that you can handle this thing by Shimura curve. So the force in the height is the one bigger piece, right? It's a vector bond of two dimension g. So I will define a small piece of dimension 1, each piece. So this usually is not that direct, but actually somehow miraculously you can do that. Okay, so I will cover the first part. The first thing is the decomposition of Fulton heights. So recall that the Fulton heights is given by a formation line bundle of the I use this notation with some metric there. And we know that the OE acts on this bundle. So, and we know that when OE acts on this bundle, we have some types, right? So naturally, so for each tau in phi, we can define the piece of tau to be omega of A tensor on. I mean, this is a big variety, so maybe we're doing something. Let me write on a fixed K. The fixed K contains all candidates of E, and such that all A phi has a good reduction defined. All are defined over K with smooth model. A. So for this case, we just fix this one part. A equals A phi. But my construction here should be more general. I build a variety with multiplication by some random integers. So first I define the piece of that is the tensor product of OL, OK, but the base here is OE tensor OK mapped to that. Because the top below the phi, you define morphism from OK to OE to OK, then you check the further extension. So this is the part. So you define a piece of that. So this will be a line bundle on is alignment of K, and you have a nature morphism from one line model to others. So we have a nature morphism from omega A to the tensor product of tau inside phi of omega of A and the tau. But they say, well, man, now I can use this one to do some decomposition, but this one does not have nature commission period, commission metric, so this is not going to work. What you're going to do is, well, that's the common sense in mathematics. Usually, if you want to get some numbers, you always take a dual thing. So what I'm going to do is, I will do same thing for dual eigenvalue variety. So I have A is the dual eigenvalue variety. Then I can form the same morphism for dual eigenvalue variety. I can form a new thing. So omega A, tensor omega A dual will go to tau phi. But dual eigenvalue variety has a type. This type is the conjugation type of omega of A of tau. Tensor omega of A dual of tau C. C is the Colmez conjugation. Amazingly, this one has a canonical metric. This has a canonical metric. I'm going to describe for you. So this individual one does not have, the dual one has, but this is normal in mathematics. So that's the whole point why every time you study objects, you always bring the dual in the future. So I'm going to describe this dual metric for you. This is probably nothing surprising. That's why we call it a polarization of a variety. A polarization of a variety, don't remember, is also a commission metric angle of variety. Right? So if you think of another way, polarization is a bring a variety to the dual as an algebras. As a different geometry, bringing the commission metric and your variety, which will induce a metric in the tangent bond or cotangent bond. So there must be some way to do that. In fact, so for accumulative base, sigma k, we have the following way to write down the variety. Is remember if you just write an exact sequence of homology, will be defined by H1 of A sigma of C over A sigma divided by H1, I'm not going to write down there, A sigma 2 pi I of Z. Right? I keep 2 pi I here to the lower the weight, otherwise the weight of 1, then we're going to weight next to 1. Now, this is the picture you have, the following. So, the cotangent bond of A sigma, of course, is a dual of this thing. Right, I will start here. In this paper, I have two different dual. One is dual in hydrogen theory and algebra geometry. One is dual just like bundles. So I just try to use star as a dual of the bundles. When I have A here, we need dual of the same variety. So it's not completely the same. For example, I have to raise. You have to raise this thing, right? So in other words, if I put this thing for this one, it's not the linear dual. I have to twist by Taylor twist. So the difference is by Taylor twist. And then this one we know is by Hartley decomposition is H01 A sigma of dual. And the Hartley decomposition has a counter conjugation, so this becomes omega A sigma. The anti-homomorphic form is a dual. So this is canonically isomorphic to this one. So what does it mean? Does it mean there is a canonical commission period between the differential forms of A and the differential form of the dual? So there is relation, a perfect. Pairing between omega of A sigma and omega of A sigma dual to the complex number. But you also can do this by more complicated method. For example, there's two varieties of the temporary bundle. You can use one class of temporary bundle to write down the duality. It doesn't matter there. So this is much more direct way. Right? And but if my linear variety has a complex application, then we induce a pairing between A sigma of tau or omega A sigma of the tau C. Okay, so this one is the line bond I care about it. So I have this line bond, so I give a name for this one. So in this case, we have a different notation, omega, this A tau is defined to be this bundle, and tau of A dual of tau C with this measure right down there. So this is a measure information line model. Okay. Great. So we created some permission line bundle. And we have a morphism of two permission line bundles. So there is this construction. There is a construction. So there's a morphism of two line bundles, omega A permission line bundle dual to the tensor product of the tau of omega of, let's write about here, A of tau. Right, so this is a permission line bundle. There are two permission line bundles, so we can do something. So the first one, we prove a theorem. The first theorem we will prove in the paper. It's not really hard to do that. So you can. This is basically the height of this thing is h5. The highest distance is also h5 because the volume of the height depends on type. Not only depends on type, because when you compute volume of height, you are really working on number field. So it's really conjugated class of type. Right. So the dual variety is definitely the type of phi C by definition is the same conjugacy class. So we compute height here, you really get the same thing.
So you have two measures, right?
What?
This side, the number with the measure is defined.
Both of them have a measure.
Yeah, but they're different measure.
Different measure.
First you give a number with a measure.
Yes.
And now you use this area to get a measure.
Right. So I have the same this morphism is isometric. Yeah. So okay. So they define isometric. Let me define some notion of the. Do I define something? Okay. Then before doing everything, let's give a definition. Definition is height of A tau is defined to be the 1/2 of the degree. Of course, I need to normalize this in degree, maybe Q degree of A tau, right? Because I trust that. And then one proposition I proved. In our paper is this definition. Well, we decompose this and depend. We pick up a different varieties to decompose. But in fact, this decomposition does not depends only on the type you choose. This actually depends only on the type. So the type have two types. I have a phi and the top inside here, right? Okay. So I can write down this one, write phi to be the cosine joined with tau, right? So I can define this one. I can rewrite this in, right? It as h cosine and tau. So cosine is the same type, but only have t minus 1 elements. Tau is a one full element. So then we have the first formula, decomposition formula for the height to the small piece. So there is the theorem is, so the for height h of phi minus summation, you decompose the phi by the two pieces tau, and the cosine, you get h cosine of tau. This one actually is pretty easy to calculate. You call it 1 over e phi over q and the log discriminant of phi and discriminant of phi c. So this is the reflexive of phi. This is the discriminant of phi. So the phi is a trace map. So somehow you can define that it's not like a linear map. So you can define the discriminant of the trace map. But you cannot define it globally. You have to define the discriminant of a type locally, right? So when I'm going to describe that, then I just said that to prove the theorem, I first need to decompose the portion type of small piece. Now I want to regroup this piece. Regroup piece I define. So for our partial type, cosine of e of degree g minus 1, as we do here, I define the height of cosine of the 1 above h cosine of tau plus h cosine of tau bar. So this one is the two CM types extending a partial type. Okay, so then what do we really prove in the paper is about the partial type. So let me write the theorem. So this partial type is a very funny thing, right? I mean, have a CM field. I check only the partial bit. Then we can show that the partial type is in fact does not depend on the type at all. It's given by 1 over 2g of L prime on F eta 0 eta of LF 0 eta plus minus 1 over 4g, well, this is minus 2, 4g log d of F. Okay? So this is actually pretty surprising because, I mean, the Colmez Conjecture is about average, all the things. We didn't use all phi's. We just take one phi, we decompose a small piece, then we take a partial type, we add a little bit, we get this thing. So this formula is very similar, of course, it implies Colmez Conjecture, but Colmez does not imply this one automatically. Right? Because we didn't use all types. We just use like 4 types only. I do not quite understand this thing, but I realize this fact of the proof. Okay, so this is the first step. So I manipulate the bottom height. I cut it a small piece, group them. Nothing there, right? Okay. Second part I will use. Second thing is I can clear that. You can compute. So now I put the unitary marker. So somehow, so this per psi, remember, this h per psi is almost like h of h phi. I mean, two types, phi 1 plus h phi 2. Let me see. Let me try. If I remember, this is the definition here. Right? You fit the psi into two types. Somehow, you can compute. The h of the psi a single linear variety. A0 isolated to A phi 1 plus sum A phi 2. So the phi 1 will be the phi 1 phi 2 will be the partial type expanded. And I also want this one to be a morphism by O of B. So in fact, this will be true. The height of this end, A0, is exactly equal h of A phi 1 at first like a talk here plus h A phi 2 talk here. So this is give us a lot of flexibility. So not only h per psi can be independent of the type you choose, also you can compute it by any abelian variety, which is isolated to this end. So in the following, what I'm going to do is to pick up a very special abelian variety, the work on it. So I fix a Hamilton base, fix the tau at the real number, and the B of potential algebra of F, the ramification set of B is a tau and some finite cases. So in other words, there's a potential algebra is indefinite at the tau, will be definite at other places. Then I assume that the E have invented the B, right? So in this case, B will be E plus E times J of x equals x bar over J squared is in F. We have this model. So then I pick up a OB maximal order. I want to contend for B. Okay, maximal order. So in this way, I can form a abelian variety by the following method. Form abelian variety A0 to B. This is B. Some Hodge structure I'm going to define later on. Some Hodge structure divided by the O of B. So the Hodge structure I put on these, and the thing is the following: the B has a Q of real number has two pieces.
Wait, sorry, I can see the speaker.
Yes.
Yeah, no, good.
So I have my potential algebra. I have two pieces. One piece is in this part. Another piece is E over J and the real number Q. I will put Hydrogen structure and this quaternion algebra, such as that this one has a type phi 1, this one has a type phi 2. But recall that both phi 1 and phi 2 are CM type extended by partial CM type cosine. So I get this abelian variety. So this is the one we're going to use. But this abelian variety will define will be a special point. So this A0 is corresponding to a point P inside. I run X nature because I have some Sinastro nature. Back on. So this is a Shimura curve, unitary Shimura curve. So to define the Shimura curve, then I have this picture here. I will define the Hermitian metric there. I want V to be B with cosine E. This is the Hermitian norm. The Hermitian norm is defined by the following method by E, A plus Bj, C plus Dj equals, the Hermitian, right? So you can take AC bar minus B D bar J squared. So this is E. So I define the Hermitian norm. Once the Hermitian norm, you calculate your unitary group. I will calculate the similarity of this group. V, I only care about the connected component. So this actually is given by delta F cross, modulus B cross, and E cross. Okay? And this one acts on V is given by the following. B, E, and the X is given by since my V is a left E major, so I get EX B inverse. Okay, so that's the action. You check this action, that's the unitary, is the unitary space, the Hermitian space over E of dimension 2. So I use this one to write down my Shimura curve.
You said that.
Okay.
Wait,
So
question. You said that B was unramified at all points but one. I think you made that. You said that B at all Archimedean places but one.
One Archimedean place.
It's unramified.
Freedom one Archimedean place of tau I picked.
That's not what you said.
Then
you said it was
Archimedean place I don't care.
So that's not what you said. You said it was.
That's what I said.
You said it was ramified in one place.
Okay.
Okay.
Yeah. It's pretty hard to find one quaternion algebra. I hope I can create one like that. Okay, so I'm not going to. That's what I said? Okay. I find a little bit weird. This is normal, so I'm not really sure that's what I'm saying. Okay, so the complex structure H, the complex structure V of R is the Shimura data that H of Q G of R, right? So in this case, we can form a Shimura curve as basically as before. Maybe it's K, compact group, sorry. And this C should be let me write down, give a name, call this one G, okay, by the G here, G of Q. Actually, the complex conjugation class of H is actually as ordered to the Hungarian alpha plane of G of Q bar. Okay, so you get this thing. So this actually parameterizes the tier type abelian varieties. You have abelian variety, you have anamorphism, you have the polarization, you have level structure. Okay. So this A is abelian variety. Of course, this is defined over the reflexive field over there. So over some scheme over E reflexive field. So this is abelian variety of S. dimension. Let me calculate. This is 2t, and you have iota 2 over E equals anamorphism of A of S. So this is going to be type phi 1 plus phi 2. I really need that we calculate the trace and calculate the sense. So I'm not going to write down there. Because this one is basically the trace, the morphism. So it makes sense. The lambda will be some polarization from A, the A dual. I'm not going to describe. I mean, to do everything probably in the paper lattice. So this will bring the Rossetti evolution will give a respect and E cross will give the conjugation. Then you have a level structure. So this will be compatible with the psi E. But psi E is a summation norm. Then you define psi Q of x and y to be the trace E over Q x squared lambda x and y equals the trace B over Q of lambda x y bar. So the E will be f squared lambda x and y and B. So you got a synthetic form there. That will give you the polarization everything. Great. So I spent so much time to talk about this unitary Schumburg variety, and the reason I do that because I want to make a connection between this omega, so that A over x, we have ax given n. Ax is the universal of unit variety. So I can define the line bound n to be omega ax tau tensor omega ax pure or c. So now the question is, you try to extend this one extend this thing and write this in again to integral models. Over O E of this thing, but unfortunately, it doesn't matter what you're going to do. You will have some trouble to study the integral models of the unitary Schumburg curve, and you probably get an integral model may not be smooth, right? But fortunately, we are in the Schumburg curve case. We have much better method to do that. What can you do is I will do it. I don't do this thing. I will do it. I will work. I don't want to work directly by a modular problem. So I will not. We will work on the quaternion Schumburg curve instead. The reason is this integral model may not be regular, and this case is regular if you choose the level very well by work of Twinkle, Sardanit, and it was non-split case by Correllon at the split case. So I will not going to talk a lot. So now I will just write down how to construct this Schumburg curve. So I have a Schumburg curve X defined by purely much better direct method of U. So this is a Schumburg curve. And this Schumburg curve is parameterized the Hodge structure and B is a real number, but is a type that have a Hodge structure. You have direct sum of vi, the pi equal to v times the real number, the f of tau I. So this has a high structure of type of negative 1, 0 plus 1, 0 and v1 and on of 0, 0 and vi. So presumably this is not there. You will not get a T. This is not a high structure for identity variety. So what we're going to do is you tensor there. You tensor to rewrite this in. You tensor E itself, E to the real number. Right? We have a higher type aside. So you get the E1, E2, EG. Here you can use a Passai. Here you have a type 0, type. So that's amazing. Aside, that's a partial type, I can use to do that. But B is a real number. This is itself is already a vector space of E. Right? So you can rewrite this as a tensor product of B to the real number. E over real number. E over real number. Right? So this one you're gonna type how to type by this set. So it's the H0. So this one H1 is basically the Passai. This one can be 1, type. So in this case, you get a morphism from two product to Shimura curve and Y to X nature. Right? So this one is a Shimura curve, a Shimura variety dimension 0 defined by Passai. Okay, so in this way you transfer everything to the Passai. So then the integral model of X will give you integral model of X, this one. So finally, we reduce the computation to the following picture. Then we write my main theorem. Then I can finish. The theorem will be the following. Assume no finite place of F ramified in both E and B. So in other words, you have many ways to choose B. Then this H cosine, H cosine is equal to HL of P. So this L is the Hodge bundle on the some integral model of the quotidian Shimura curve. The P is the special points fixed by the equals. So this is what I can say is the YZZ, the Gonzaga type formula. No, this is not Gonzaga. So we do this part. Then what's left? What's left is the Gonzaga type formula. This is not sorry. I'm confused. Okay, from here already get H cosine of H about P. And here, to rewrite the formula, is given by negative LF of 0 eta, LF 0 eta, minus plus 1/2 log EB over D of E of F. So this one I write in the YZZ formula. In the Gonzaga type. So finally, so that's the formula I reduced to. So we reduce to some calculation on the quotidian Shimura curves. Once the quotidian Shimura curve I don't think I have time to describe that. Maybe, okay, I have next 2 minutes, so I can describe what are the proof here. It's the same method to prove usual closed-Array formula. You have one side analytic kernel, other side geometric kernel, then you can get difference. And when we prove closed-Array formula, what we do, we try to show that this difference is perpendicular to all custom forms. But when we prove the Colmez conjecture, of course, I mean, in that case, we don't care as statistics at all. When we prove Colmez conjecture, in fact, I mean, if you only work on a custom form, you throw a lot of junks to trash. You don't care about that. But what kind of the Colmez conjecture, you have to bring all the trash back. So we got another 50 pages to dealing with the trash. It's only recycling of the trash. In the paper of this YCC paper, this annals of math studies. So when you get this paper and all the trash you can bring back, that gives you Colmez conjecture. Okay, sorry. I just
Maybe let's start with Paris. Do you have any questions from Paris?
No questions from Paris.
Okay. Then, any questions from Tokyo?
So you use integral model. So any integral model will do, or you have some special model?
So I use integral model. Okay, so I need an integral model to handle the deformation. You remember, I mean, the one I'm doing is invariant differential forms is naturally fit into the Cordero-Spencer map. So you need to have a good integral model to handle the Cordero-Spencer map. And unfortunately, at unitary level, unless your P is a good prime, you will not get a good Cordero-Spencer. So there's some error there. So that's the kind of estimate. I believe everybody will for arbitrary one, you have such a problem. But Quaternion Shimura curve, what do? You don't have identity variety, but you have all the divisible groups. So you still can define that the Hodge decomposition is a Gauss-Bonnet connection to study the Cordero-Spencer map. So that's the reason I moved from unitary one to the Quaternion one. So in other words, somehow I construct integral model for the unitary Shimura curve, but it's already a problem. Even you have regular and OF, we can change the nature of the singular. So I really don't know. I mean, anyway, it's a much better work on the potential Shimura curve to study the Cordero-Spencer map. Also, another weird thing is that the Cordero-Spencer map in the literature most of them are wrong because some literature. They messed up between the cotangent bundle and cotangent bundle, because there's a homomorphism. So we really do very carefully to study the Cordero-Spencer. So that's the reason I needed that.
Thank you.
More questions?
Yeah, that's it from Tokyo. Thank you.
Okay, so finally, any questions from Beijing?
So for average, so you choose the average case, so can you recover for any extension case, can you recover the Colmez proof by using this proof structure?
Very good question. So you're asking what my next project.
Okay, because you have an actual proof structure.
Okay, so I believe I didn't find that. If you work on a U21 instead of U11, you should get everything. But that needs a lot of work, because first thing, you needed to, you needed to work really hard on RTL theory and the Shimura curve both. And RTL theory says we needed to solve some one question, which is I still don't know how to solve that, is construct the harmonic forms. the periodic harmonic forms on a line bundle. So if you line bundle with a square of curvature, this is like a Claude type problem. The uniqueness Xinyi Yuan and I did it, and the existence is not very clear. So after that is done, then we have some hope. You see, when I do this, do you remember I do the combination of psi tau, tau bar added together? If I have the unitary term U21, what I can do is h twice of tau. So if I can do this one and the unitary small variety on unitary of U21, I should be able to compute the formula h tau psi twice plus h tau bar psi. Right? So I get this is a U21. And this is a U1. The U1 give me formula h tau psi plus h tau bar psi. So you see, I take a difference, what I get? So wait for next year.
So, any more questions? Sir, no questions, then let's thank the security.